today here. And what we try to do together with my colleagues, so my name is Willem van den Heuvel, with my colleagues Erika, Kumara and Damien Tamburi, who are not yet in the room because they are involved in a session, a Destiny session. Destiny is a European project, it's a collaboration between Sapienza University Rome, the JADS, where I'm working, which is a joint venture between the Technical University of Eindhoven and Tilburg University, and of course the Cyprus University of Technology. So we have a satellite event ongoing this week, and that's one of the reasons that you've not seen me so much over here and participating that much. But this will change completely for today, since I will be around as the chair of today. And what we have tried to do in our team, and yes, all three of these guys mentioned on the slide are affiliated to JADS, is we try to come up with an interesting program that revolves around blockchain, smart contracts, and services. Now what you will see is that at the end of the day, we have had some last minute changes, and I will walk with you through the agenda later on so you know what to expect. But we have had some last minute changes, which means that we couldn't place as much as emphasis on the smart contracting blockchain side as we wanted, but nevertheless, I think we have a very interesting program, and I invite you cordially also to make it as interactive as possible. I realize that all of us have mails, that we are sometimes working on new project ideas, new paper ideas, which is absolutely perfectly fine, it's normal. I'm also doing it myself sometimes, but at least let's try to be, let's say, active and interactive in some of these sessions, which will be given today. So I won't talk too long, because we have as a first speaker, we initially had Athanasios, who's working these days at ASML. ASML is a pretty well-known company in Europe, at least in the Netherlands, is very well known. It's a daughter of Philips, and a company that focuses at the development of machines, produce machines for computer chips. He would have talked about his experiences with data products, but unfortunately, due to some personal reasons, he had to cancel last minute, which meant we had to come up with a replacement, which at the end of the day I found in our team, which is a guy sitting at my right-hand side and at your left-hand side. It's Athanasios Angelakis. Yes, he's one of the great guys in our team at JADS, and he will talk about data quality enhancement via data completeness with an OSM paradigm. Athanasios is an interesting guy. Aside for being involved in JADS, he has worked for Huawei. And these days he's also part-time working for Harvard Medical Center in the US. And then he will talk about a topic which revolves around the theme of smart cities and data quality. Next, we already have a coffee break, which is good. I'm very Dutch, maybe without using coffee. I miss it now. And after that, we'll have a presentation given by Dennis. I won't pronounce his last name. I will have to exercise a little bit for that during the coffee break. We'll do it. We'll do a short rehearsal, and he will talk about the topic of data management and blockchains. And then we hit into, I'm always expected here, we hit into the lunch break. And after the lunch break, we have a little bit of promo. We have some guests from Italy. We invited from a company called Astrocode. I'm working quite closely together with Astrocode. It's a very cool a company who develops a low-code IDE that accommodates a model-driven approach to develop blockchain-enabled applications. And we have been involved in a couple of European endeavors and adventures with them. After that, we have a guest from the University of Hawaii who also works part-time for CMU. You might know him because he has been involved in co-authored some books on software architectures. And he will do two lectures, in fact. One of the challenging architects web 4 systems, and the other one is on architecting machine learning enabled systems. After that, we're getting late in the afternoon, and I still hope we'll hold on for the paper sessions, and we have a couple of very interesting ones, which I guess we will discuss later on in the afternoon. So let's slowly get started. So Thomas, maybe you can get here so we can start with your presentation.
Yeah, okay.
One, two. So, good morning, everybody. I'm Athanasios Angelakis, and thank you for the introductions that already explained. I will try to wake you up. The first talk and the last in the conference, from my experience, is the high risky ones. You don't have to get bored from this day, you don't have to be really tired of the last one. So I will talk about the data quality enhancement via data completeness, and I will explain about the OSM paradigm. It's a work which already have been deployed. I will spoil a bit, at least in 30 countries in the world, and now we're writing down the paper appropriately. So I'd like to discuss about, as you know, the increasing of the data generation and usage as regards the also quality. They have been raised, they have been concerns that have been raised, and they have been keeping researchers busy for many years. So it's not only Andrew and ONG who initiated the whole data-centric AI last year. Up to now, you know that we have the data wherever they come for any kind of distribution. And then the last 10 years, let's say, with the explosion of CNNs, we would like to use this data to create amazing models to outperform whatever we have been used so far, like general, conventional, let's say, statistical approaches. But last year, ONG initiated the data-centric AI. LeCun followed a couple of months ago, publishing 2 papers already on this thing, and I'm going to discuss about data-centric AI approach and a particular paradigm. The concerns vary from managing the quality of the data itself, so managing the quality, to reducing potential biases that data may bring. We all know about bias by human beings, specifically when we talk about data sets that have to do with human beings, like not in genomics, but AI radiology, for example, it's a really concrete example with medical doctors. They tend to get biased after a while as soon as they start feeling comfortable with using an AI tool to improve their flow or their report. But this is a different kind of bias, and I will discuss about it in a few slides. So, as I already mentioned, the data-centric artificial intelligence, or DCAI, field aims to improve the data understanding and quality of data used for machine learning models. So that's something that I initiated last year. Data quality concerns, and what are we going to do? We're going to discuss about volunteer geographic information, which are applications focused on creating a geographical database that's editable by contributors. We know that if you have worked a bit in computer vision, or you see around, or even if you drive a Tesla, you can drive around, using many kinds of different data sources, where your car understands in a way that it can drive by itself. So in order to do that, you need some fundamental data, which are crucial. And one of the most fundamental data that you need is the speed limit. So I'm going to discuss about it. But of course, all this raises questions, and then we start wondering about what kind of quality, how good is our data. So we will talk about the OpenStreetMap data, which originally developed to provide free access to share and edit geographic data, and it has been grown to one of the largest open source geographical databases. It's used by many different companies, among them, some of them are biggest tech companies in the world. So if you go, for example, to Google, to Apple, to Huawei, to all the big guys, to Amazon, that they create in general maps, even TomTom, of course, OSM is free, so everybody takes advantage of free data, right? Data is power, and if it's free, it comes with no price, then you are happier. So most of these companies, they use it, but they do not actually say they use it. Data quality assurance for OSM data has become an active research area, developing methodologies for checking, assuring, and improving the quality of OSM data. And of course, this makes sense, because if something is open and anybody can contribute to it, so you can go outside here, you can take some notes, and you can say the speed limit outside the hotel is 3 kilometers per hour. Nobody, somehow, nobody will ever check it. The only thing would happen is if I will go after 2 days or after 1 hour, and for the same exact road segment, I would say this is 4.2 kilometers per hour. And this is my ground truth. So imagine starting building models, creating smart cities using this kind of data. Okay? So from the geographical perspective, high quality data solves incompleteness and positional inaccuracy. High quality data will benefit machine learning algorithms in making more accurate predictions on geographical tasks. Everybody, hopefully many of you have already used Google Maps, going from A to B, give me the shortest path. I don't want to go from mountains, I would like to go from lakes. Doesn't exist yet as a feature. Probably in the future, I would like to have reduced CO2 emissions, for example. It's something that Google has been introduced. So how all these things work? Good data quality, actually, is something that we use in estimated time of arrival prediction, going from A to B, how much time it will take. And traveling salesman problem, route optimization, all this kind of stuff that every day we use in our lives without even considering what's happening behind. So quality concerns is focused on the keys present for each of the entities in OSM. The keys here I'm describing a bit of the OSM for you that you are familiar with. So keys provide metadata that describes geographical entities, and many machine learning applications are being developed on this data. And actually, many machine learning applications meaning they're in production now and it's running. Even though OSM data is updated on a daily basis, the quality is not certain to increase over time, right? So many people, we would like to create free data, we would like to live in a, let's say, free world that everybody can take advantage of our shared knowledge, but at the same time, it doesn't mean I won't be trying when I will input in your data, right? So, as identified by many studies, data quality suffers from contributor subjectivity, and that's also always the case. So several OSM contributors have actively focused their attention on creating quality assurance tools for contributors to check and update the data. So up to now, what has been done is like there have been some communities, let's say, that they have dedicated themselves to the quality of the data. For example, if outside the hotel here I'm riding 4.2 kilometers per hour with the maximum speed limit that I can drive, I can check if I want, if I have time, if I would like to contribute from satellite images from two consecutive times the same vehicle drives from A to B outside the hotel, how much time it took it, right? So then I will check if that's correct. But also I have to take into account what actually is the minimum speed limit that it's permitted in Greece, and particularly in Crete here, right? Because I can say 1 kilometer per hour, but you will never see a sign with 1 kilometer per hour. So there are many things that someone could check. OSM contains many different entity classes, road segments, buildings, points of interest, and here we focus on a subset of them, namely the road segments, since it's high importance in ETA prediction, TSP, route optimization using machine learning. So far, models have been developed that are able to help users fill the specific need for higher data quality standards. We provide a solution to data imputation of geographical metadata for road segments in OSM in a fully automatic way for any country in the world. So what we've done, we developed a methodology that imputes the missing values for two keys that are related to road segments, namely the maximum speed limit and the number of lanes. Both keys are used extensively in ETI, mainly ETA, TSP, route optimization. The main part, which is one of the, I will try to keep you up to the last moment of my talk. I would like to question yourself if someone could do data imputation when the feature is missing 92, almost 90% of its data. So if you would like to create a machine learning model, you're missing 40% of data. There are some things you can follow to fill in, like a mean or median or whatever, which is really the easiest thing you can do. But actually, there have been research on that, and some guys they use it. But then the question is, how much data do I need to start considering a feature in my model if I'm going to use it or not? It's really important, a feature. I know that because, for example, we're working in AI in radiology and we're examining livers, right? And someone has fibrosis, so it's acute cirrhosis, okay? So then you know the size of the left lobe is bigger. You know this feature. But actually from 100 patients that you have, only 30, they have this measurement. So what are you going to do? Are you going to use data computation there? Are you going to use the mean for someone that, you know, if you drug him, maybe he will die? Actually, he will die, and she will die. But there are many questions that are raised if you start doing data computation and if you really need the feature, right? So, therefore, the following question will be answered. Can we improve the data quality of the keys for all segments in OpenStreet map? And the things like how data computation and in which sense it will help us improve the data quality and fulfill the completeness task that we have for this particular kind of data set. So then we separated the following questions. First one is, can we impute max-peak values for OpenStreet map data? Can is a question because we don't know. 41% is a really big percent, right? And of course, if we can, how accurately? How accurately means it's good to write a paper and it's good to initiate a research, but if actually I would like to put it in production, because OpenStreet map data is not only for research, actually we used to put models in production, right? So if yes, how accurately means, is it production ready at the end? Can we impute the number of lanes, and if yes, how accurately? So let's talk about what has happened, and I will explain a bit more about the data-centric stuff and about the OSM data, which is a really high importance initiated last year. So while the increase in machine learning performance is mostly attributed to the development of new machine learning algorithms, data quality concerns have been receiving more attention. This is started by Jordan 2015. The current neural networks really heavily rely on regularization. By regularization, here I mean data augmentation. While this often boosts performance, over-regularization actually creates a model that's unfair across classes. This is a work, there are two papers, the second one, so the inability to understand the regularization effect is leading to bias in machine learning. Just to describe here, let's say you would like to classify 10 classes of birds, right? And you have a limited data set. So you want your model to understand better, it's a computer vision model. So you do data augmentation techniques, so flipping, rotating, whatever. And you do that before even try to understand the data set. That's actually something which we do. We take for granted that if I have a data set, I will use a machine learning algorithm, I will have some specifications, it's going to work, and I'm happy about that. Well, actually, this is not the case because Belleschiero is a team in LeCun. So these two papers by LeCun that came in last February and last April, a couple of months ago. And actually, they say that if I do by randomly rotation, so to all of my exams, I will apply a vertical flipping, for example, it will boost the performance of the model, but actually, some classes don't have so good performance, so it's biased against some classes. So data collection has been identified as a major bottleneck in the progression of machine learning in multiple communities, while there exist multiple different fields related to it. While the fields can differ significantly from each other, when you're looking at the papers of the field, they all share a common goal. So this is improving data quality. So here, it's a really nice diagram that has to do about data governance specifically. So you have the data collection, then you go to data acquisition, data labeling, existing data. And then you can see many things where actually we would like to automatically change some stuff in order, for example, if you use the existing data, improve data and improve model, so make the model robust and we have transfer learning and all this kind of stuff. I put it there because it's really good if someone is interested in this particular really nice graph. Sorry, again, it comes from Rob, 2019, about checking what kind of data sets we have. So papers have been published which show the impact of wrongfully used data or lack of data understanding. Missing or incorrect data is one of the largest compromises to the decision process downstream. That's why Andrew NG last year, he started taking by hands the companies and say, guys, okay, you have data, you have a model that goes there, it reaches this level of performance, but actually what we would like to do, check your quality. So 3 data quality dimensions introduced by Latin in 2009. And this recognized the multidimensional nature of data quality, and this is based on problems with data quality on levels. And then I'm explaining them. The first is the extensional data quality, which focuses on the data values comprising criteria such as accuracy, correctness, timelines, and completeness of data. The intentional data quality dimension, which comprises criteria concerning the content and the conceptual schema relevance, clarity, definition, the scope, the level of the detail, as well as the consistency and flexibility. And the last one, and this is something that we're dealing with in this research, is data representation addresses data quality problems related to data format, interpretability, portability, and deliverables. So, research uses of benchmark datasets called started in 2021 among different influential research papers and machine learning communities, and they found that within the period of 2015 and 2020, the majority of the community relied on the same benchmark datasets. Over 50% of 43,000 sample datasets correspond to datasets introduced by one of 12 elite Western institutions. You know that there are companies like Google, Amazon, and Meta, for example, that because they have the resources, right, and they have people driving around taking photographs, taking videos, so they create data sets. But of course, you have to imagine that these guys really increasingly about the revenue in their companies, right? So if I create a huge data set that everybody will use it, I'm getting citations, but at the same time, I show to my competitors that I did a really nice job as regards this particular data set. So it's not completely unbiased. They also show that for certain tasks related to facial recognition, the majority of researchers make use of ML data sets that they are inherently biased. They found that some data sets are being used across communities for tasks that the data was not intended to be used, by resulting in completely conflicting conclusions. It doesn't mean when I read a paper that what it says is true. I always have to check the metrics about the model, the robustness of the model in so many ways that I will really be sure that this could go to production. The issue of data quality assurance is prevalent among many machine learning research communities. Now, as regards the BGI project, sorry, how much time I have?
You still have about, if you wish, half an hour.
All right, okay, so I'm going. So this is not, I hope it's not boring, but I'm really not initiating, but I'm really trying to share with you here the concerns about, don't take for granted the data set which is somewhere, we download, we do everything with it, okay? So in VGI projects, the data is provided by volunteers. We saw the motivation behind using something with geographical information. This is something what motivates someone to do that, right? We discussed about 3 different methods about data quality assurance. This is crowdsourcing, the social approach, and the geographical approach. The geographical approach to this kind of data is supported by the first law of geography, which I didn't know about it, from 1970 from Tobler. It says, all things are related, but nearby things are more related than distant things. And this is actually what we use. For example, if you have in your mind KNN algorithm, this is something that actually this guy uses, right? So the geographical approach for VGI data quality assurance, introduced by Guchai in 2012, allows for the interpolation of unknown values by making use of information on the geographically close entities. So, and again, I'm going outside the hotel, I would like to go down to the beach, and I see the sign, the OSM data, which says 4.2 kilometers per hour. Then I'm walking a bit, 300 meters, and then I check again, and it says 10 kilometers per hour. And then I continue walking again, so I'm just 700 meters from the beach route, it's 1 kilometer in total distance. It's the same road, doesn't change, the ID is the same in my data. And then again I see 4.2. So if you create, for example, like NNN there, it should understand that with 3 consecutive segments for the same ID road, it should have consistency, right? It should be consistent, the kilometers per hour. So if I see a 4.2, a 10, and a 4.2, by voting, by example, I say it's 4.2. Just imagine something like that. Due to the rise in VGI data, they also publish different metrics to assess data quality, the different notions of data quality regarding geographical information. Completeness is one of these metrics that's particularly applicable in the case of the OSM key data. As mentioned before, this notion of completeness is part of the extensional data quality dimension, right? So it was the third part of the data quality that we discussed. And completeness has nothing to do with the algorithmic completeness that we know. Completeness as regards the degree to which a given data collection includes data describing the corresponding set of real-world objects. So even if I have 100% filling the road segments all over Earth using OSM data, from OSM data, and actually this does not correspond to the real-world thing, to actually the maximum speed limits that exist, then it means that this is not a good thing. The data set is not complete. And finishing, regarding the OSM data quality, one study was performed in 2011 by NICE, and they used the OSM data available in Germany and compared this to paid TomTom data available at that time of the research. TomTom is a Dutch company, it's huge, probably you know. They create amazingly high definition maps. So they compared something that was in production and they had customers with OSM data, which is a really nice comparison. The method for the comparison was relative completeness, as we discussed, and they found that the OSM data in overall was 27% more complete compared to the TomTom data, right? In total. But if you would like to check what was happening for car navigation data, which was the specialization of TomTom at that time, it was 9% more complete compared to OSM data at that time, right? So the OSM data was lacking. In which part was lacking was the metadata for road segments. The problems with the OSM data identified in 2010 and 2011 have one important thing in common. They both highlight the issue that the OSM has with semantics and road segments. OSM has named these semantic attribute keys and allows the users to submit information to existing ones or create new keys, as we discussed before. Completeness is lacking. So here you see, like, from chronological evolution of both the max speed and the number of lanes, and now starting getting into the data of the problem over the past 1.5 decades. You can see that even though there's a clear incline, that info shows that these two keys, max speed and number of lanes, are not present in 1.72 and 1.58 of all the roads documenting their steps. So if you go, for example, take Cuba, and you would like to see the max speeds there, right? So the road segments. What is the completeness now? What's the percentage? You will see that the missing values could be 95%, 97%. An example, since we are in Greece we are not well known that we do something for free. So if you go to OSM for Greece, you will find the only area which has OSM data up that I checked a couple of months ago was in Thessaloniki and not the whole Thessaloniki. So we don't have any data for Greece in OSM, right? So it's almost zero. So, and then you can see this is a research that presented in 2018 as regards the completeness of three-quarter road tags. You can see the green one, it's the maximum speed, and you can see different cities in Spain. So Granada has 8.27. We talk about a small percentage of data, and then that's why it's the question if that's enough to do the data imputation. Now we will talk about our approach. So first we have we downloaded the PDF file from GeoFabric and translated the CSV, and we initiated the whole because we had to choose a country. We chose Netherlands because let's say it's really well structured. You can find you know what kind of maximum speed you have to many road segments from the data from the government sites. The feature that we used for our models was the ID of the road, the max speed, the road type, the number of lanes. If a street is two-way, the length in meters, the longitude start and the latitude start of the node, of the two nodes that define a road segment, and the longitude end and the latitude end. So the IDs used to identify the roads from one another, but of course you have a road and then you have road segments. The road segments share the same ID. Here you can see this is from the government. This is the speed limits that are allowed, and you can actually not allowed, but you can see in signs in streets in Netherlands. 5, 10, 15, 20, 35, 30, up to 130. You will never see a 32, you will never see a 4.2, you will never see a 1, you will never see 900 kilometers. Because I will explain there are some crazy values there, everybody can put the value, right? So if you start cleaning the data set, you can see whatever crazy outliers. So you understand, like, this is the whole distribution. This is of the max speeds of the data that they have values, of course, right? So now if you go to the number of lanes, as you can imagine, there are also some streets which have 6, and actually you can drive with 30 kilometers per hour, and why that's the case, that was really crazy one. But actually, it's a 6-lane street which drives to a port. So all the cars are standing there, they cannot drive more than 30 kilometers per hour. But then, in order to check the data, we actually had to use Google Map to go to the particular coordinates and check if this is an outlier or not. So that's the distribution, and here you can see the number of lanes, the max speed. Yeah, I put them there just if someone would like the slides later on. So here are the features, the values that we have for the categories of number of lanes and the max speed kilometers per hour in the Netherlands. And this is actually the final data set. So missing before processing, we mean like cleaning, whatever, drop out the duplicates. So it's more or less the same. For 43.10, it's not the same number because some is missing. But again, we have to do data imputation for the max speed, having only 43%, and number of lanes having just around 8% data. So for the list of different max speed values and the number of lanes, what we did is replace all values with integers and delete all not allowed characters. Values that do not have an integer are replaced with missing values. So what we want to do is actually we don't push ourselves to understand what's happening in the data as regards the cleaning stuff, right? I mean, there are some outliers who are interested, but in general, if something was not so clear to us why it's there, why it has this value, we just throw it out and we say this is a missing value, okay? I mean, if you're missing 33% and you go to 43 and you go to 45, yeah, it's not a big deal, right? If you're missing 92 and you go to 93, well, it's more or less the same. So we checked if for each value it's contained in the list of known values set by the Dutch government for maximum speed limits and number of lanes. And again, values that they were not there, we just excluded them. We replaced the original values for maximum speed and number of lanes with the corrected values. And after removing, we have this kind. We talk about Netherlands. It's a really small country. And you can imagine for Netherlands, we have 3.5 million of data that we have to play with and create machine learning model that actually we have at the end to update the OSM dataset with that, right? First, what we deal with data imputation of the max speed, and then, if the result is good enough, we will proceed following the same methodology as with the max speed, adding the max speed as feature. So, it's two projects actually. The first one was you try using, well, you go for the best case of the two bad cases, right? So you start data imputation with max speed limits, which you miss 43%. If this is the case and you succeed and you have a really good result, you can apply your model, you can take the predicted values together with the ground truth values that you had, you can use as feature to the next project, which is data imputation for the number of lanes, which is missing 92%. So you need all the information that you will have. Of course, someone would say it could have the impact of the error, right? So, but this is something that we will not deal with that. So imagine if you have a road network, and when we talk about smart cities in general, what we talk is about a graph. A graph as defined mathematically it has vertices and edges, right? So that's how you see the whole problem. And why you see the whole problem like that? You would like to take advantage, as I said, of algorithms that run on graphs, clusterization of graphs, for example, to understand better what's happening in the whole network, right? So everything you do it in a graph. And using the graph, we create just two more features, which is what is the degree of the node. So you have a road segment, you have a node which identifies at the beginning, and the node that defines actually the segment. And then you say what's the degree in the graph of the node which the edge starts, and what's the degree of the node that the edge finishes at the end. Why you want that? Imagine you go to a highway with 130 kilometers per hour, and somehow you have a link to this highway, right? So the link, it could be crazy to have 30 kilometers per hour maximum speed limit. It could be 80, sometimes it could be 100, maybe 90, 110, but 30 is really outlier. So you know, this is a road segment, right? So if you take the node which has 3 degrees, because you have 3 edges there, one will have 130 kilometers before, the next one will be 130 kilometers, and the link will have 30. So you really, if you take the local correspondence, the local information, you really have to take advantage of that. And there's also research previous in 2010 that shows that. So the final feature that we use is the ID, the maximum, the ID of the road, the max speed road type, number of lanes, and then we just added the degrees. And here you can see plenty of them have a degree of 3, some of them 4, but actually there exist some which is 5, right? Now we're going to the good stuff, enough from the not boring, but really data intense, I would say. Now we go to the actual part, which is the action of how we deal with the whole thing, what were our experiments, and what we wanted to do at it, right? So as I said, maybe I didn't say, no, I didn't say. So OSM data, every day it's updated, right? So if you want, and that's what we would like to do, if you would like, using automatically, just give the input the country, and then from the government for each country, which is a pre-processed step that you will have to check. What are the maximum speed limits and the number of lanes that are permitted in this country? What would you like to do given only these features? Would you like to have an automated process for every country to automatically update every day the whole thing, and at the end you don't miss data in maximum speed and number of lanes, which you know is crucial for everybody on Earth. We know we help also companies, that's part of the deal, but for humanity we will have something that everybody, 100% if you would like to continue research on that and use whatever he wants to use, right? So the whole thing is like, take the OSM data, which is an override, create the missing values from the bad user input, right? So you do the data cleaning. But at the end, I would just want you to see, you have to go here. And that's the whole thing, and that should take place in just a couple of minutes, right? So data, problem definition, data, and infrastructure is something that we always do care. That's the triangle when we want to have something in production. Okay, if the infrastructure changes, the model will change. So we have also constraints about that. So we check the data against the government data, right? If everything is okay, we process the data, and then we start with splitting. So we did 3 splits, and actually that's one of the most valuable ways to check if your model is robust enough to go to production and not to write a paper. I'm pointing that out. So we split the data at the beginning in the training test. As we know, 95% and 5%, we have 3.5 million, 5% was more than enough. But then we took the train set and then we split it again in 80 and 20. And why we did that? We wanted, and as we did, we checked 3 different regressors, and I will explain the whole problem and the approach. Intent for close validation in the 80% of data, and then apply these hyperparameters which have been tuned to the 20%. These numbers, the metrics that we use, which is mean absolute percentage error, root mean square error, and mean absolute error, but actually we're using MAPE. it should be similar. Now, from this, we have to choose one of the models that we have tuned. And if we are okay with that, then we will go and we will apply this model to the 5% of the test data. And also this number should be similar to the previous two numbers. If and only if these three numbers are really similar, then we are with high probability certain that the model is good enough to go to production. Okay? So, we train this classifier. As you can see, we go with random forest because that's the smartest guy. So depending on the infra we have, we wanted to try random forest that has been research that actually works well with this kind of data. Of course, if you have a local information, you always use a bit of K and M to see how it will perform. And since CalBoost is really, you get on the blog from 2018, it's an amazing algorithm, it's a creative boosted tree, it competes with XGBoost and LiveGBM. We also wanted to try CalBoost. And we did the whole thing, we evaluated the model performance, and then we go to predict. Actually, here is like something I would like to mention. If you have, this is a multi-classification problem, right? We have 15 different classes that we would like to predict the missing values if they belong there. So, but if you take, if you see a classification problem, a multi-classification problem, as a classification problem, and you really need the information about the difference between the classes, whatever difference this is, as regards some numeric value, right? Some metric, for example, then you don't deal with the classification problem, you deal with a regression problem. It is different to have an error in 130 kilometers of 5%. It's different to have an error of 5 kilometers of 5%. As regards the impact this error will have to my results. So what actually you do, you say, I will go for a regression, so I will translate the whole thing to a regression problem, and I will deal with a regression problem. After I have my regression model, I will have to use a decision tree, some thresholds, to map back my numeric to actually the classes, right? And as soon as I do that, do I have to do something to improve? And actually, we did something to improve the whole thing, and I will explain later what was that. So first we have the prediction, then we go to aggregate mean of predictions, and that means at the beginning you have the whole road segments, but you can have 100 road segments with the same ID, they belong to the same road. At the beginning, you don't know that. You don't take advantage of this local information. Only you take advantage during the modeling. But as post-processing step, you would like to take advantage of that. So you have 100 road segments that they share the same ID. Then you take all the predictions there. You take the average, and then you say, this is what is going to be the label for all of the 100 road segments. So the local information is not only for the model, it's also as a post-process step, right? And then at the end, you go to the rounded aggregated predictions, and this is actually the decision tree at the end, which you have to find a way how to map back the numeric values you have in a really nice way to the classes. At the end, finally, you are happy, and you go to the predict, you have the results, and then if all the numerics are good enough, all the scores are good enough, then you have the imputed data. So 43% you used, 57% you have now with a really minimum error, and then you upload to the OSM data updated with a flag which says, so as we imagine, we haven't collaborated yet with OSM because first we would really like to write a paper. This is a joint work with Cyprian Wildeburg, a master's student of mine, and the idea is to have 2 data sets every day for each country. One would be without our, without what we're doing, and the other would be with data imputed stuff, right? So now we go to the numbers, just to wake you up. So this is the testing and the numbers about the road segments. Here is the decision boundary that we took at the end, and this is the ensemble model, the whole thing. Right at the end, you have to create something. So we say, okay, With a close 0 to 5, everything will be a 5. With 5 open up to 12.5, you will map it to a 10, and then you do the whole thing. And question here, you will see this rule that we did after analysis, how much it helped the model as a post-process step, which is an ensemble model at the end, to improve the model, the results of the model, the performance of the models. Number of lengths, similarly. So here are the first results. I'm finishing. So we have the model of random forest, KNN, and CalBoost. We did a lot of tuning, but random forest was the best. Just a remark, in bibliography, they claim KNN is great on this kind of data. And actually there are also some papers that they say it's not so good as you say, and actually we showed that it's not good KNN. Best is random forest, and then comes gradient boosted trees. So the mean absolute percentage error after the 10-4 cross validation in the 80% was 0.055. This means, like, if you are 100 kilometers and the ground is 100 kilometers, you have a 5.5 error, right? So you could go with 105 kilometers, you could go with 95 kilometers. Yeah, there's no problem. There's not even a police there to do anything to you, right? And even in 100 kilometers. So production rate, actually, when we were using it, we had the mean absolute percentage. If it was less than 8, less than 10, actually, it was ready to be in production. So then this is a result about on the test set on the validation, actually, which was at 20%, and you can see the scores. It's similar, so 0.055, 0.059. So you are happy, and here is something interesting. Here, the first is the results on the test set. So now we talk about the test set, right? So here we have the 10-4 cross validation on the 80%. Here we have on the validation, which was the rest 20%. These numbers are similar, so we say, okay, let's apply our model to the test set, to the 5% we will have excluded from the beginning. And the 0.056 is the performance on the test set. After aggregating and put them all together, it didn't change. 0.56, right? So 100 segments, everyone shares the same value, so you say 0.76. But if you use the decision tree with the thresholds at the end that I showed you with the intervals, the error reduced 21.43%. 0.056 and is reduced to 0.44. So this also shows, and that's actually part of the discussion, like, don't just say, I will have any kind of data. This is something that I think is pretty clear today. I will use algorithm and machine learning algorithm. I will tune it a bit. I will have a result and I'm happy about it. It's not that easy. And at the end, actually, if you continue with error analysis and you create some ensemble, you will see, of course, it has to do with the data that you have, that the threshold could drop down 21.43%, which is really huge for this kind of low error. Similarly, this is extensive. Go to details. This is the mean absolute percentage error per category. But I think I'm out of time. Just to discuss about the number of lanes. Similarly, you see random forest outperforms all the other guys, 0.125. Again, cross-validation, 0.127. We talk about so close, right? It should be so close. Otherwise, you have problems about overfitting, underfitting, and other kind of things. But we don't want to go to production having these kind of issues. Some companies they do. And at the end, you also see here, like we apply the threshold, the ensemble, and with post-processing, the error has been reduced from 0.1230, which was not production ready, to 0.091, which is production ready. So we make our managers happy, and our customers even happier. Now, we just checked if you take a mean, you could see really some papers, they say just take the mean and do the imputation. This is out of discussion. Sorry, 2 minutes. Yeah, thanks. This is out of discussion in general. So you create arguments about that. In our case, if you just take the average of the training set of the speed limits and you apply, you will see an error of 0.432. Okay? So, number of lanes, similar thing. And final slide. So, what we did, we developed a methodology that computes the missing values for the two keys that are related to road segments, namely maximum speed and number of lanes. Both keys are used extensively in ETA prediction, TSP, route optimization. The main obstacle in this work was the high percentage of missing values, 41.10, 91.9 before processing. And then we have the questions. So, can we improve the data quality of the keys for road segments? As regards completeness, which we have the metrics and the scores, we can. And of course, we have the full data set with really reduced errors. How? If we can, even with 43% of missing data, yes. It is production ready, it is production ready. Can we do the same thing for number of lanes? Yes, we can. It is production ready, it is production ready. That's it. Thank you very much. I hope you didn't get so much tired. Any questions?
So we have room for a couple of questions.
Yes. No.
Maybe
I should.
we have another one here. Wait.
Thank you. It's a very interesting presentation. I was wondering about, first of all, very impressive that you can do these kind of things with 92% of data missing, right? And I was wondering, can you extend this approach, this algorithm, this machine learning approach, also to other data? Does it work for any type of data that you can model as a graph?
Thank you, Stefan. That was a really nice question. That's a really nice question. If you translate the data set in a similar way as you said, with you have to transport your data set, you have to project your data set, and in order to do that, you have to transform your data set in this kind of features. And then, yes.
And the features, it's nodes and graphs, right?
Yes, nodes and edges, but they share, yeah, I don't mean the...
But which share characteristics?
But they share, so you have, one crucial thing here was the road ID, and then you have, I think, right?
I have another one.
Oh.
If you can argue that the node shares some similarities, you can apply.
Yeah, so one crucial thing here that it took advantage, the machine learning model, and also us as a post-process was like, we knew you have the road segment with 100, you have this road, which has unique ID, and then you have 100 road segments, for example, you share the same ID, but you have 94% of data missing there. So that's the local information, and that's really important. The things like, there are also different categories that are crucial, and we're working on that. But yeah, the first thing is that if community wants to use this thing, which we hope, I'm pretty sure they won't use, yeah, and then we can continue. Thanks.
There's time, I have another question, but I don't want to take away.
There's another question over there.
Thank you for the nice talk. You mentioned production readiness. So what does it mean? Can you elaborate on that?
Yeah, production readiness, in general, when you put something in production, and when I say something in production, we talk about guys like Google, Huawei, that they use Google Maps, Petal Maps, and these kind of things. This particular project, I was working with Huawei, and we have been implemented in 30 countries. Not the same, but not the similar thing, of course. But production ready, it would be good enough to go if you have for max speeds less than 5% or less than 10%, because then actually you never go with 130 kilometers, but there will be some exceptional cases that if you do, then you have already 10% of problem. But 5% were actually what we would like to achieve. So then you could go and put it in production. So every day, if you use Google or if you use Petal Maps, these things there. So there are some SLAs, some specifications that you have. It comes from the company, it doesn't come from anyone, right? So depending on the product you have, of the product readiness that you have, you specify this kind of metrics, right? So yeah, that's what I said. It's not only for research. It goes to production. So any other question? You can find me here outside. I will be more happy to discuss. Yes, sure.
Just one last question. Did you investigate which features had highest weight in the prediction?
No, we didn't do that.
Visual work.
Yeah, we didn't use any. Sorry, we used random forest. Yeah, we could use shape values, but we didn't use that because the performance and from the error analysis that we did, not for feature engineering, not feature performance. But actually what we've done, we reduced the error. So we didn't do any feature engineering. Not at all. Right? We didn't do any polynomial, degree, something or whatever, square root, nothing. This is just a raw thing, and that's also part of the computational power. Random forest I was really happy because it's a quick guide and you can have it in production, robust as you saw. So the whole thing works. That's but maybe for future, but from the performance, we don't actually need to investigate further this kind of thing. Nice question.
Yeah. And basically your premise was that OSM data, you use OSM data for training your model, right? You test training statistics and so on. What makes you confident that the OSM data is actually promising, that there are true values in it? I mean, you split it and you use.
Yes, that's a really nice question. That comes from my experience working in companies like that. So I can tell you, when we investigated in Netherlands Google Maps going from A to B, and we're using OSM data and now travel metrics, we were much better than Google. OSM data are better from Google Maps in particular cases, and overall we use both OSM data and actually this production. Coolblue use this every day to deliver stuff. PostNL use every day to deliver stuff. Huawei uses to deliver stuff, plus with TomTom data. That's actually part of the question that you have to check the quality of the data, which actually was happening up to now, and actually you have to check by satellites, and other people's data. But what we did is we take for granted this is okay. So for future work, to reduce the error and to make it even better, you have to actually create some post-process steps that check. And that's part of the whole thing, but it will take a bit to explain how actually this is just the first thing. What you do, you don't start with 43%, we start with even 90%, and then we reduce, so then you create iterative the whole thing in order to check at the end if the performance is okay. And if you have a minimum amount of number of data, which actually have the same performance, then probabilistically speaking, you have really minimum error, that there are errors in the data from the beginning that you started with.
Yeah.
But that's the next step. Yeah. Thank you very much. Thank you very much. I hope I woke you up. I will be around, so you will have to answer questions. Cheers.
Okay guys, so we have a coffee break now for about 50 minutes, and after that we have a very interesting talk from Dennis about data management in blockchain. So please be back in 15 minutes. Vamos.
advertising